outputting a number, completely blind to the messy, beautiful, abductive reality of true human thought.
Imagine, if you will, a machine so brilliantly engineered that it can flawlessly beat the world champion at the incredibly complex board game Go.
Right, yeah.
I mean, it anticipates moves, it recognizes these like beautiful patterns, and it just completely dominates a human master who has studied the game for their entire life.
Oh, absolutely crushes them.
Yeah. But then you take that exact same underlying intelligence, right? You put it inside a 2-ton vehicle in your neighborhood, and it completely mistakes a bright yellow school bus for a snowplow.
Right, or, it drives straight into the side of a white tractor trailer because it actually thought the truck was the sky.
Exactly. It sounds like a paradox.
It really does. I mean, it sounds like a bad joke, honestly. But it is the sobering reality of modern technology right now. We are engineering these systems that are capable of apparent, superhuman genius in one specific domain.
Yeah.
But then it's coupled with this shocking, almost comical blindness in another. And, well, the gap between those two realities isn't just a matter of needing faster processors or, more data.
Right. It's not a hardware issue.
No, it's a fundamental crisis in how we define reasoning itself.
Which is wild. And that massive disconnect, that canyon between mastering a board game and just surviving a drive down a chaotic city street, that is exactly what we are going to explore today.
Yes, it is.
So welcome to this deep dive.
Yeah.
Our mission today is to unpack a highly specific, philosophically dense, but I mean absolutely critical set of ideas. It's rooted in a chapter titled Problems with Deduction and Induction.
It's just a phenomenal starting point because it forces us to look past, all the daily headlines about the latest AI models and travel all the way back to the foundations of human epistemology.
Right.
If you really want to understand the invisible walls that currently constrain artificial general intelligence, or AGI, you have to understand the architecture of inference.
Okay, let's unpack this.
Yeah.
Because here's the blueprint for you, the listener. We are going to walk step by step through the two foundational pillars of logic. First, we tackle deduction, which is the pursuit of absolute mathematical certainty. Then we pivot to induction, which is the messy, probabilistic way we learn from experience.
And we are going to dissect how these two ancient philosophical concepts are entirely dictating the absolute limits of machine learning today.
Because we have to start at the historical beginning. I mean, if we want to understand why a multi-billion-dollar neural network struggles to navigate a physical street, we have to look at how human beings first defined correct reasoning.
Absolutely. And for that, we turn to Aristotle.
Right, going way back.
Way back. He essentially kicked off the formal study of inference thousands of years ago. He was trying to solve a massive problem, which was, how do we separate a convincing lie from a demonstrable truth?
Because people were just arguing rhetorically.
Exactly. He wanted to lay a structural foundation for what it actually means to reason correctly, independent of the subject matter. So he developed a simple structural form of deduction known as the syllogism.
Now, anyone who has taken like a basic philosophy or logic class knows the structure of a syllogism.
Oh, sure.
You take two statements or premises that you establish as true, and they lead you inevitably to a third statement, which is the conclusion.
Right.
The classic example, the gold standard we all know is, all men are mortal, Socrates is a man, therefore Socrates is mortal.
And the beauty of that structure is its inevitability. I mean, in Aristotle's tradition, for a system to be considered intelligent, it must conform to these known deductive rules.
Right.
It's about structuring thought so that if your starting points are solid, your endpoint is logically guaranteed.
Yep, but there is a crucial distinction we have to make right out of the gate to understand why classical AI failed. We have to separate valid logic from sound logic.
This is so important.
I want to focus on that because our sources give some brilliant examples to separate the two. A lot of people conflate validity with truth.
They do all the time.
But validity is just about the structural integrity of the argument, right?
Right.
It's like it's the pipe the water flows through.
That's a perfect way to look at it, yeah. Validity is just a stamp of approval on the mechanism. It essentially says, if the premises are true, the conclusion must be true.
Right.
But it doesn't care if the premises are actually true in reality. For instance, consider this argument. If it's raining, pigs will fly. It's raining, therefore pigs fly.
Right. Structurally, that is flawless.
Flawless.
It uses one of the oldest deductive rules discovered, known in formal logic as modus ponens.
Yes.
Basically, if P, then Q. We have P, therefore Q.
Flawless validity. The mechanism preserves truth perfectly. The problem, obviously, is that the first premise is a complete fiction.
Yeah, pigs don't fly when it rains.
Exactly. So the argument is valid, but it is not sound. Soundness is the ultimate, much higher bar.
So soundness means the premises have to actually be real.
Right. Soundness means not only is the logical structure perfectly valid, but the premises are factually, empirically true in the real world. The Socrates example is both valid and sound.
Got it. And then, of course, you have reasoning that doesn't even bother with validity, like the fallacious stuff.
Oh, yeah.
The sources highlight a great, almost lyrical example of this, which is Ray Charles is God because God is love and love is blind.
It's so good.
It's play on words, right?
Yeah.
Since Ray Charles is blind, the flawed logic tries to map him to God. It completely ignores the structural rules of deductive reasoning.
Right. And a machine programmed with pure deductive rules would instantly reject that Ray Charles argument. It would flag a syntax error in the logic.
Because it doesn't follow P to Q.
Exactly. But it would happily accept the flying pigs argument as valid, pending verification of the premises. And what's fascinating here is how intoxicating this kind of structural perfection was to the early pioneers of artificial intelligence.
Let's talk about those pioneers. Because I always think of deduction like a perfectly sealed mathematical pipe. Whatever liquid truth you pour into the top of the pipe, it flows through the logical structure and comes out the bottom without leaking a single drop.
That's the dream.
Yeah, and if you're a computer scientist in the 1950s looking at the brand new invention of the microchip, this is exactly what you want. You want a sealed pipe. You want certainty.
You want something perfectly computable. John McCarthy, who helped found the field of AI at the legendary Dartmouth Conference in 1956, he launched this massive, decades-long effort to develop what they called knowledge-based systems, or symbolically driven AI.
Right. Good old-fashioned artificial intelligence. Go FAI.
Exactly. Go
yeah.
FAI. The premise was simple and just breathtakingly ambitious. They thought, well, human intelligence is just the manipulation of symbols according to rules of logic.
Oh.
Therefore, if we can just encode the entire physical world into these symbolic deductive rules, if we can just write down enough, if P, then Q statements, the machine will be able to reason perfectly about anything.
And it wasn't just a pipe dream. Right. I mean, they had immediate mind-blowing successes that made them think they were on the verge of solving intelligence entirely.
They really did.
We're talking about programs like The Logic Theorist, created by Alan Newell, Herb Simon, and Cliff Shaw in 1956. This wasn't like a chatbot.
No.
It was a program that took the foundational work of Bertrand Russell and Alfred North Whitehead, their massive, dense mathematical treatise, Principia Mathematica, and it automatically proved real, complex mathematical theorems.
It was incredible because in formal logic, the rule if P then Q is called a material conditional, usually written with an arrow. P arrow Q.
Right.
It is entirely analyzable. The early computers were essentially physical manifestations of these logic gates. The machine just follows the arrow. If the premises are fed into the system, the conclusion is absolutely guaranteed. It is completely bug-free on a theoretical level.
Okay, but this raises a massive glaring contradiction. If this method is completely bug-free, if it guarantees truth, and if we had software proving complex theorems in 1956, why didn't we achieve artificial general intelligence in the 1960s?
Right.
What is the catch? Why isn't my toaster debating philosophy with me today? If deduction is the gold standard of human reasoning, why did classical AI hit a brick wall?
Because the very thing that makes deduction perfect in the realm of mathematics and formal logic makes it practically useless for navigating the messy, chaotic, unscripted reality we actually live in.
Wow, okay.
Mathematics is a closed system. The real world is an open system. And when you try to force the open world into the sealed pipe of deduction, you immediately run into two fatal flaws.
Let's tear into those flaws, starting with what philosophers call the knowledge problem. This is the idea that deduction is actually a massive illusion when it comes to discovery.
Yes. The knowledge problem states that deduction never, ever adds new knowledge to the world. It is entirely tautological.
Meaning it just repeats itself.
Exactly. It only makes explicit what is already hidden or assumed inside the premises.
Even in the Socrates example, right? If my premises are all men are mortal and Socrates is a man, I technically already possess the knowledge of his mortality before I even run the deduction.
You do.
I am just unpacking my own suitcase. I haven't learned anything about the universe I didn't already encode into the system.
Precisely. Deduction gives you a fantastic defense against making irrational, contradictory leaps, but it is sterile. It doesn't help you discover new physics or, read a novel situation.
Right.
More importantly, it merely shifts the burden of proof away from the logic and onto the premises themselves. A perfect logical structure is useless if the premises are hotly debated.
The sources outline a fascinating historical example of this, involving Ptolemaic astronomers trying to defend the geocentric model, the idea that the Earth is the center of the universe.
Yes, against the rising tide of Copernican theory.
Exactly.
A Ptolemaic astronomer in the 16th century could build a perfectly valid deductive argument. They could write, Premise 1, if the heavens were created by God, the earth would be placed at the center of the heavens. Premise 2, the heavens were created by God. Conclusion, therefore the earth is at the center of the heavens.
Again, flawless modus ponens. If P, then QP. Therefore Q. You cannot attack the structure of that argument.
You can't. It's perfectly valid. But all the heavy lifting, the actual agonizing debate over what is empirically true, is just shoved into those premises.
Yeah.
How do you objectively prove God created the heavens with the earth at the center? A scientific materialist would reject premise 2 outright. Galileo might reject the theological interpretation of premise 1.
Right. He famously noted that the scriptures tell us how to go to heaven, not how the heavens go.
Exactly. Deduction offers absolutely no mechanism for resolving the truth of the premises. It just processes them.
I see this constantly in modern discourse. Conspiracy theorists often make zero deductive reasoning mistakes.
Oh, their logic can be incredibly tight.
Yeah, they just start with completely deranged premises. So if you program a machine to run on pure deduction, it is fundamentally trapped. It can only process the knowledge we manually code into it, and it has no independent mechanism to verify if that knowledge accurately reflects reality.
And that leads directly to the second, even more devastating flaw of deduction, which is the relevance problem.
Here's where it gets really interesting. Because even if you somehow manage to feed a computer millions of perfectly true, perfectly sound premises, deduction still fails. Because deduction has absolutely no concept of what actually matters.
The philosopher Wesley Salmon provided a brilliant, slightly absurd example to illustrate how blind deduction is to relevance.
I love this one.
The argument goes like this. All males who take birth control pills regularly do not get pregnant. A man takes his wife's birth control pills regularly. Therefore, the man does not get pregnant.
Okay, let's stress test that. Structurally.
Yeah.
Perfectly valid. But more than that, it is completely sound.
Yeah.
The premises are factually true. Biological men who take the pill do not get pregnant. This specific man took the pill, therefore he didn't get pregnant. It's 100% mathematically, empirically true.
It is entirely true, and it is entirely irrelevant.
Right.
The man's avoidance of pregnancy has absolutely nothing to do with him taking the pills. Men lack the biological anatomy to get pregnant regardless of what medication they ingest.
But a classical AI, right? A robot armed with a vast database of facts, reasoning purely through symbolic deduction, would look at that argument and think it had perfectly logically explained why the man wasn't pregnant.
It would. It doesn't understand that the pills are disconnected from the outcome because it doesn't understand reality. It just sees the logic gates closing successfully.
Because it lacks any concept of causation.
Exactly. The sources give another example that drives this home involving an arsenic poisoning. The coded rule is anyone who eats a full ounce of arsenic dies within 24 hours. A man named Jones eats an ounce of arsenic. Jones dies within 24 hours. The deductive conclusion is that the arsenic killed him.
That seems like a solid deduction.
Yeah.
He ate the poison, he died.
But what if Jones ate the arsenic, panicked, jumped in his car to speed to the hospital, and was instantly killed in a horrific traffic accident?
Oh, wow.
The deductive argument is still perfectly sound based on the timeline. The premises remain true, but the conclusion that the arsenic chemically caused his death is wildly misleading.
Because deduction doesn't differentiate between a true correlation and a true cause.
It can't. Relevance presupposes an understanding of the physical mechanisms of cause and effect. A deductive machine doesn't know the difference between an actual causal driver and a coincidental truth.
Right.
If a thermometer outside is glowing bright red, it is hot outside. That's a true statement. But if you ask an AI to explain why there is a heat wave, and it points to the red thermometer, it has totally failed to understand physics.
But the thermometer doesn't cause the heat.
Exactly. A rooster crowing doesn't cause the sun to rise.
Let me push back here, or at least let me ground this. We were talking about roosters and birth control, which are fun philosophical thought experiments. But the sources we are unpacking take this lack of causal understanding and apply it to a deeply sobering real-world catastrophe.
They do, yes.
They use this exact framework to explain the Boeing 737 MAX tragedies.
This is where the limitations of rule-based logic stop being a philosophical game and become a matter of life and death. In 2018 and 2019, two Boeing 737 MAX aircraft crashed, one in Indonesia and one in Ethiopia, resulting in the tragic loss of 346 lives.
Yeah.
When crash investigators and systems engineers look at a complex catastrophe like this, they don't just find one simple deductive rule that was broken. They have to untangle a massive, multidimensional web of proximate and distal causes.
Let's define those for the listener. Proximate meaning the immediate physical trigger of the event. Distal meaning the background, systemic or structural pressures that created the conditions for the trigger.
Exactly. So what was the proximate cause of the 737 MAX crashes? It was a software system called MCA, the Maneuvering Characteristics Augmentation System.
Right.
Due to a faulty angle of attack sensor, the MCA incorrectly assumed the planes were stalling, and it aggressively pushed the nose of the planes down, overriding the pilot's physical inputs.
But if we want to understand why this happened, we can't stop at the software glitch. We have to trace the logic back. And it is not a simple A to B line. Why was MCS there in the first place?
To understand that, you have to look at the distal causes, the design constraints. Boeing had redesigned an older model, the 737-800, to fit larger, more fuel-efficient engines.
Okay.
But aerodynamics dictated that to make these massive new engines fit without scraping the runway, they had to be placed further forward and higher up on the wings.
Which fundamentally changed the physics of how the plane flew.
It did. This physical placement meant the plane had a tendency to pitch its nose up during certain maneuvers, which could induce a dangerous aerodynamic stall.
So the MCS software was essentially a digital Band-Aid.
Yes.
It was put there to automatically push the nose down to counteract the pitch-up tendency caused by the new physical engines.
But the causal chain goes even further back. Why use a software Band-Aid instead of just designing a brand new airplane from scratch?
Right, why not just build a new plane?
Because of intense corporate pressure. Boeing was in a fierce, existential market rivalry with Airbus, who had just released the highly efficient A320neo. Boeing needed a fuel-saving aircraft quickly to retain market share.
And crucially, a massive selling point of the 737 MAX to airlines was that it shared the same type rating as older 737s.
Exactly.
Meaning airlines wouldn't have to pay for expensive, time-consuming simulator retraining for pilots who already knew how to fly the older models.
Therefore, Boeing downplayed the existence of MCS. They didn't require rigorous simulator training for it, meaning the pilots in those cockpits were not adequately prepared to handle a runaway MCS failure.
So here's where it gets really interesting for you, the listener. If reality is like this Boeing example, a tangled web of aerodynamics, market share battles, pilot psychology, and sensor failures, how could a deductive machine ever map this out?
Can't.
It can't. You cannot write a mathematical rule and if P then Q statement that perfectly captures the tension between Airbus's stock price, engine placement geometry, and software design.
You absolutely cannot. The philosopher Plato imagined a universe of perfect forms. In Plato's universe, a triangle always has exactly 3 sides, and the internal angles always equal 180 degrees.
Right.
You can write perfect deductive rules for Plato's triangles. But the real world isn't made of perfect triangles. The real world operates on shifting context, on hidden variables, on overlapping contradictory pressures. Deduction demands that variables be perfectly true or perfectly false.
But the real world operates in the messy gray area in between.
Exactly. And because deduction failed so spectacularly at handling this messy reality, scientists and engineers eventually hit a wall. The era of good old-fashioned artificial intelligence, with its encyclopedias of hard-coded rules, stagnated. The Aristotelian dream died.
Yeah.
So the field pivoted to a completely different paradigm to try and achieve intelligence.
They abandoned deduction and they embraced induction.
Yes.
Okay, let's transition to induction. Because if deduction is about starting with a top-down rule and finding certainty, induction flips the entire process upside down.
It really does. Induction is the process of acquiring knowledge from experience. Instead of starting with a grand universal rule, you build bottom-up from raw data. You observe particular individual instances in the world, and you synthesize them to form a general hypothesis.
Our sources note that the primary mechanism of induction is enumeration, which is really just a fancy academic word for counting.
It is counting instances. You observe an event once, twice, 1,000 times, and you begin to generalize a rule based on the frequency of those observations.
I want to highlight a massive difference here between the two pillars. We established that deduction doesn't add any new knowledge to the world, but induction is synthetic.
Yes.
It actually adds to our knowledge base. It allows us to generate new hypotheses and, most importantly, it gives us predictive power.
Predictive power is the holy grail of intelligence. The examples given to illustrate induction are so mundane, they beautifully highlight how entirely dependent the human mind is on this type of reasoning.
Like what?
Well, if I know that traffic is always backed up at the intersection of 3rd and Main at 5:00 p.m., I didn't deduce that from the laws of physics.
Yeah.
I induced it because I have sat in that traffic 100 times. I formed a predictive rule: avoid that intersection at rush hour.
That makes total sense. Or if I reach for the doorknob on my front door while looking down at my phone, I don't calculate the spatial geometry of the door.
No.
My past experience, my physical enumeration of thousands of times opening that door has created an inductive hypothesis about exactly where that knob is in space. My hand just finds it.
The entire scientific method is heavily reliant on inductive reasoning. We observe thousands of swans over centuries, we note that they are all white, and we induce the biological rule, swans are white.
Right.
We observe biology on Earth, we note it all relies on carbon, and we induce the rule, all life is carbon-based. We count the features, and we form a universal category.
This mechanism scales up to power almost everything in our modern world, particularly statistical generalizations. If you flip a fair coin 1,000,000 times, you expect it to land on heads roughly 50% of the time.
Exactly.
If a political pollster surveys a random representative sample of 1,000 voters and finds 73% prefer candidate X, they induce that candidate X will get roughly 73% of the actual multi-million person vote.
It is incredibly powerful and incredibly flexible. But there is a massive epistemic trade-off.
Always a trade-off.
Always. What you gain in flexibility and predictive power, you lose in certainty. Because induction relies entirely on observation and sensory data, the knowledge it produces is always provisional.
Provisional meaning it's basically an educated guess.
Exactly. Inductive generalizations are just highly educated bets that the future will resemble the past. There is no logical guarantee, only statistical probability.
Think about your own content feeds right now. The algorithm running your YouTube homepage, your TikTok, or your news app is an engine of pure induction.
Oh, absolutely.
Our sources dive into this exact dynamic. The system observes your past behavior. It counts your clicks. It says, okay, out of the last 100 articles this user engaged with, 75 of them were conservative political commentary. Therefore, the algorithm induces a rule: this user wants to see more conservative commentary.
It is a statistical prediction based entirely on historical observation. It projects yesterday onto tomorrow.
But what if today, right now, that user suddenly decides they want to challenge their worldview? What if they actively search for an article from a progressive outlet like the New Republic?
The inductive system will likely bury it or filter it out.
Right. It traps you in a mathematical echo chamber of your own past behavior. It fundamentally assumes you cannot change.
Which brings us to the devastating trap hidden inside induction. It is a trap that philosophers have been warning us about for centuries, and it is the exact trap that the multi-trillion-dollar AI industry is currently tumbling headfirst into.
We have to talk about the problem of induction.
It is one of the most famous problems in philosophy, most sharply articulated by the 18th century Scottish philosopher David Hume.
Okay, what did Hume say?
Hume was looking at how humans formulate beliefs, and he pointed out a terrifying flaw in the foundation of science itself. He showed that there is absolutely no rational, logical guarantee that instances of which we have had no experience will resemble those of which we have had experience.
Right. Just because the sun has risen every single morning for the last 4 billion years, there is no mathematical or logical law that absolutely guarantees it will rise tomorrow.
Not at all.
We just have an incredibly strong psychological habit of expecting it to. We assume what Hume called the uniformity of nature.
And Hume pointed out that if you try to prove the uniformity of nature, if you try to prove that the future will resemble the past, you have to use induction to do it.
Oh, wow.
You end up saying, induction works because it has always worked in the past. It is a completely circular argument. Relying on induction requires an epistemic leap of faith.
The sources illustrate this vulnerability beautifully with the constant, maddening flip-flopping of modern nutrition science.
The great egg yolk debates. For decades, Based on vast inductive observations and epidemiological correlations, nutrition science confidently warned the public that the saturated fats in egg yolks caused cardiovascular disease.
I remember that.
It was treated as a medical fact. Whole generations ate egg white omelets.
But then, you fast forward a few decades, better observational tools are developed, larger data sets are gathered, the variables are isolated differently, and suddenly the data shifts.
Completely shifts.
And we are abruptly told to eat the whole egg because the yolk actually contains nutrients that protect against the very heart conditions we were terrified of.
It is an embarrassing scientific about-face, but it happens because inductive observations are never truly complete. You are always dealing with incomplete data. You might have missed a confounding variable. Your sample size might have been biased. The environment itself might have shifted.
I want to introduce Bertrand Russell here because he took Hume's problem and sharpened it into a lethal critique. Russell warned that if science views itself merely as an exercise in collecting and enumerating facts, it is deeply vulnerable.
Yes, very vulnerable.
And to illustrate the fatal danger of relying purely on inductive data collection, he gave us what I think is one of the greatest, darkest parables in philosophy.
Russell's inductivist turkey.
Walk us through the life of this turkey because it perfectly maps onto how machine learning works today.
The story goes like this. A turkey arrives at a new farm. On his very first morning, the farmer comes out and feeds him at 9:00 a.m. Now, this turkey is a good, rigorous scientist. He doesn't jump to hasty conclusions based on one data point. He decides to use enumerative induction. He waits. He collects a massive, statistically significant sample size of observations.
He's gathering trading data.
Exactly. He observes that he is fed at 9:00 a.m. on Wednesdays and Thursdays. He notes that he is fed at 9 a.m. on warm days and cold days, on rainy days and dry days.
He is testing his hypothesis against environmental noise, proving that the rule holds regardless of the weather. He is building an airtight statistical model based on pure, unadulterated empirical data.
He is. Finally, after months of rigorous data collection, his inductivist conscience is satisfied. He has thousands of data points. He confidently concludes, based on overwhelming empirical evidence, I am always fed at 9 a.m.
And then comes Christmas Eve.
And instead of being fed at 9 a.m., the farmer walks out and cuts the turkey's throat.
Oh man, an inductive inference built on absolutely true premises, rigorous observation, and massive sample sizes, led to a completely false and literally fatal conclusion.
Why did the turkey die? Because the turkey didn't understand the causal context of the farm.
Right.
It didn't understand the hidden, latent variables of human holidays, agricultural economics, and dietary traditions. It just saw the surface-level data points.
Yeah.
It equated correlation, the farmer arriving, with a benign cause getting fed, completely missing the underlying reality, which is getting fattened for slaughter.
So the obvious question is, if induction is this dangerous, why do we crave this kind of thinking so much? Why do humans, and by extension the artificial systems we design in our image, constantly fall for the turkey trap?
This raises an important question. Russell argued it's because the human brain is fundamentally an induction engine. We have a desperate evolutionary psychological need to find patterns in our environment, even when those patterns are complete illusions.
The sources mention the gambler's fallacy here, which I think everyone has experienced on some level.
Oh, sure.
You are standing at a roulette table in Vegas, and the ball has landed on a black number 5 times in a row. Our deeply ingrained inductive brain starts screaming at us, it's due to hit red. The pattern must balance out. Or conversely, the brain says, black is on a hot streak, the pattern will continue, bet all your chips on black.
It is a powerful illusion,
Yeah.
but the mathematical reality is that every single spin of a roulette wheel is an independent, mutually exclusive event. The wheel has no memory. The little ball does not know where it landed last time. The probability of hitting black is always roughly 48%, every single spin. But we impose a narrative pattern onto the randomness because we are desperate for predictability. We crave certainty in a chaotic universe. And this craving makes us completely blind to the fact that new, unprecedented information can utterly surprise us.
Let's challenge this, though. Let's make this practical. I survive using induction every single day. I'm not a dead turkey.
No, you're not.
If I learn to drive my car in Seattle, I observe that drivers generally stop for yellow lights, and they usually yield to pedestrians and crosswalks. I build a complex inductive model of how driving works based on thousands of hours of local data. Now, if I take that exact same inductive brain, I fly to Mumbai and I rent a car and try to drive using my Seattle rules, I'm going to cause a massive accident within 5 minutes.
Because the environment has fundamentally shifted. The underlying distribution of the data has changed, but your inductive rules have not updated yet.
Exactly. So my question is, how can an autonomous vehicle, a machine learning system that is based entirely on historical training data gathered in Silicon Valley or Phoenix, ever handle a truly unprecedented event? How does it handle a strip of nails falling off a construction truck on the highway or a line of ducks crossing the road for the very first time?
Mathematically, it cannot. When faced with a truly novel, out-of-distribution situation, induction fundamentally breaks down. In fact, as our sources point out, what you need in those critical, unprecedented moments isn't more inductive data from the past, it is less.
Wow, less data.
You need to abandon your historical assumptions to deal with the immediate novel reality in front of you.
But this feels like a massive contradiction that we need to resolve. If induction has this fatal turkey flaw, and if it completely shatters when the environment shifts, why is the AI industry dominating the global economy right now?
That is the million-dollar question.
Why are we seeing massive headlines about AI systems achieving superhuman feats? We mentioned AlphaGo at the very beginning of the show. AlphaGo used a type of induction to utterly master the game of Go, which has more possible board configurations than there are atoms in the observable universe. It crushed the human champion, Lee Sedol. How is that possible if induction is fundamentally flawed?
To resolve that contradiction, we have to look at the environment, not just the intelligence of the machine. The sources explain that systems like AlphaGo and its more advanced successor AlphaZero use a highly sophisticated technique called deep reinforcement learning.
Deep reinforcement learning. Let's break down how that actually works under the hood.
At its core, it is a form of machine learning, which means it is fundamentally just high-speed, automated, multi-dimensional induction.
Okay.
AlphaGo doesn't have rules of strategy programmed into it. Instead, it plays millions and millions of games against itself at lightning speed. It observes the outcomes. It induces hypotheses about which board states and move sequences are statistically correlated with a higher probability of winning.
It is essentially the turkey, but it's gathering millions of days of data in a matter of hours.
Exactly. And the AI research community justifies this approach using a rigorous mathematical framework called PAC learning.
PAC learning. What does that stand for?
It stands for probably approximately correct.
Probably approximately correct. I love that name
Yeah.
because it is so honest about its own limitations. How does PAC learning mathematically justify induction?
PAC learning is a statistical learning theory. It essentially proves that if you define a specific hypothesis class and you feed the system a sufficiently massive amount of data, you can mathematically bound the probability of error. It proves that over time, the system will weed out the bad hypotheses and converge on a strategy that is close enough to the optimal truth with a high degree of probability.
So the computer scientists look at Hume's problem of induction, they look at the turkey, and they basically shrug. They say, sure, philosophy dictates there are no absolute logical guarantees in induction, but mathematically we can get probably approximately correct, and in the real world, that's good enough to win.
They say it's good enough because it works brilliantly when it is confined to a game. But this is where the sources launch a fierce critique of the entire modern AI paradigm. Thinkers like Stuart Russell, a highly prominent AI scientist, point out a devastating caveat to PAC learning. These systems are achieving superhuman success on discrete, observable, two-player environments with known immutable rules.
Known rules. That is the dividing line.
A Go board is an enclosed, perfectly bounded mathematical universe. It is a 19 by 19 grid. The rules of physics on that board do not change halfway through the game.
Right.
Gravity doesn't suddenly reverse. The lighting doesn't change. A black Go piece never spontaneously turns into a duck.
There is no Christmas Eve for AlphaGo. The farmer never comes out and changes the fundamental nature of the universe.
Precisely. The training data and the test data come from the exact same unchanging distribution. The sources refer to this delusion in AI research as the lamppost problem.
Oh, this is a classic, deeply funny metaphor. Let's share it.
A police officer is walking his beat late at night, and he sees a drunk man on his hands and knees under a brightly lit street lamp, desperately searching the pavement.
Okay.
The officer walks up and asks, "What are you doing?" The drunk says, "I'm looking for my car keys." The officer looks around the illuminated circle and asks, "Did you lose them right here?" And the drunk replies, "No, I actually lost them way over there in the dark park, but the light is much better over here."
That is exactly what the AI industry is doing.
Mm.
They're looking for the holy grail of artificial general intelligence, inside the enclosed universes of video games and board games.
Right.
Not because a game of chess is an accurate reflection of navigating a messy physical world, but because the light is better. The data is perfectly clean, the rules are known, the state space is fully observable.
They have confused mastering a closed system with understanding and open reality, and this reliance on clean, bounded data leads directly to the defining, terrifying flaw of modern deep learning models: brittleness.
Brittleness. This is a crucial concept. The sources cite the extensive work of researchers like Gary Marcus and Ernest Davis to demonstrate just how physically fragile these neural networks really are when they interact with the real world.
Brittleness means the system shatters the moment you step even slightly outside the mathematical distribution of its training data. Let's look at the Atari Breakout example detailed in the sources.
Oh, I remember this game.
Google's DeepMind trained a reinforcement learning agent to play classic Atari video games, including Breakout.
Breakout is the retro game where you control a small paddle at the bottom of the screen and you bounce a pixelated ball up to smash a wall of bricks at the top.
Right. And the DeepMind AI became astonishingly good at it. It discovered strategies humans rarely use. It was hailed as a breakthrough in generalized learning.
Yeah.
But then researchers at an AI startup called Vicarious decided to test the robustness of that intelligence. They took the exact same game, but they tweaked the environment slightly. They moved the paddle just a few pixels higher on the screen.
If a human player was handed that controller, it would take them maybe 2 seconds to adjust. You would instantly recognize, oh, the paddle is a bit higher up, and you would just adjust your timing and keep playing perfectly. You understand the concept of the game.
But DeepMind's supposedly superhuman system completely fell apart. Its performance severely, instantly degraded. Why? Because the neural network didn't actually understand the semantic concept of a paddle or a ball or physics or breaking bricks.
He was just looking at pixels.
It had merely memorized the statistical geometric regularities of the pixels on the screen in that one specific original configuration.
Yoshua Bengio, who won the Turing Award and is considered one of the godfathers of modern AI, is quoted in the sources explicitly confirming this limitation. He says that deep neural networks tend to learn the statistical regularities in the dataset, the surface-level correlations, rather than the higher-level abstract causal concepts.
And this mathematical brittleness translates directly to catastrophic failures in real-world image recognition. The sources note that AI can classify human faces or breeds of cats with incredible 99% accuracy because the pixels of a cat's face are distributed in regular, repeating statistical patterns.
Right.
But if you take a photograph of a cat that the AI recognizes perfectly and you simply change the background color of the image from white to blue, its performance can completely degrade. It suddenly has no idea what it's looking at.
Because it wasn't looking at the catness of the cat. It was looking at a high-dimensional mathematical manifold of pixels. And changing the background shifted the data out of the distribution it recognized.
Exactly. And this leads to the terrifying real-world driving examples. Researchers have shown that if you take a standard red octagonal stop sign and you place a few completely irrelevant pieces of black tape or stickers on the red area, a human driver ignores the tape.
Yeah, we just see a stop sign.
They see a stop sign. But a deep learning vision system, confused by the unexpected geometric pattern, misclassified that altered stop sign as a 45-mile-per-hour speed limit sign.
Imagine the catastrophic result of an autonomous vehicle accelerating through a crowded intersection because of 3 pieces of tape.
It's terrifying.
Or the examples we opened the show with. A self-driving car's navigation system misclassifying a bright yellow school bus as a snowplow because of the angle of the sun. Or mistaking the broad white side of a turning tractor trailer for a brightly lit overhead overpass, driving straight under it with fatal consequences.
So what does this all mean for the quest for AGI? It means a physical robot trying to walk down a chaotic Manhattan street isn't just a harder, computationally heavier version of playing an Atari game. It is a fundamentally, philosophically different type of reality.
Manhattan is not Atari.
The sources state this explicitly. Manhattan is not Atari. The real world is made of exceptions, not rules.
A busy city street is defined by its abnormalities. The unexpected construction detour, the erratic cyclist, the pedestrian sprinting through traffic to catch a cab, a plastic bag blowing across the sensor array.
And if your underlying intelligence is based purely on enumerative induction, which is what machine learning fundamentally is, you are mathematically inherently blind to exceptions. You cannot predict the unprecedented.
Turkey.
You are, quite literally, a turkey waiting for Christmas Eve. The sources are incredibly firm on this conclusion. These failures are not just software bugs that can be patched with 10 times more data or a slightly faster GPU. They have fundamental epistemic limitations of inductive inference itself.
Okay, this brings us to a critical juncture. We have to figure out how to climb a new ladder, because we've established that the first pillar, deduction, is way too rigid. It demands perfect platonic triangles and fails to map complex causes like the Boeing crashes.
Right.
And we've established that the second pillar, induction, is too brittle. It shatters if you change the background color of an image or if the environment shifts. So where does this leave the science of intelligence? The sources bring in two heavy-hitting thinkers to map out exactly where we are stuck and what true intelligence actually requires.
We begin with Nassim Nicholas Taleb. He is a mathematician, former options trader, and a relentless critic of statistical overconfidence. He wrote extensively about risk, probability, and the illusion of certainty.
Okay.
The sources utilize his framework of the four quadrants of statistical prediction to explain why AI is currently dangerous.
Let's walk through Taleb's quadrants. It's a matrix that categorizes the types of decisions we make against the mathematical structure of the environment.
Quadrant 1 is simple decisions in an environment with thin-tailed probability. Think of things governed by a standard bell curve or normal distribution,
Like what?
like predicting the average height of a group of humans. Extremes exist, but they are bounded. You aren't going to find a human being who is 3 miles tall. Anomalies don't ruin the statistical model.
Quadrant 2 is complex decisions, but still within that safe, bounded, fin-tailed environment.
Right. And quadrant 3 is simple decisions in a fat-tailed environment. But Taleb argues that the true danger, the domain where history is actually shaped, is the fourth quadrant.
The fourth quadrant. Complex decisions coupled with fat-tailed probability distributions. Let's explain what a fat tail means mathematically because it destroys the premise of machine learning.
In a fat-tailed distribution, often related to power laws, rare extreme events are significantly more likely to occur than a standard bell curve would predict. And more importantly, when these rare events do happen, their impact is so massive that it completely dominates the overall data set.
A great example of a fat-tailed environment is wealth distribution, or the stock market. If you put 100 average people in a room, you can calculate their average net worth. If Bill Gates walks into that room, the average net worth skyrockets to $1 billion. The single anomaly completely destroyed the previous statistical average.
Exactly. The fourth quadrant is the domain of stock market crashes, pandemics, and unprecedented geopolitical events. It is the domain of the turkey problem. Taleb points out that our modern overconfidence in induction, our reliance on past data algorithms to predict the future, actually exacerbates the catastrophic impact of these fourth quadrant events.
Because the algorithm looks at the last 10 years of stock market data, which was relatively stable, and mathematically guarantees that tomorrow will also be stable. It cannot predict the black swan.
We get locked into machine thinking. We optimize our supply chains, our financial models, and our self-driving cars based on the averages of the past, leaving us completely structurally vulnerable when the unprecedented occurs. The sources warn that building an inductive superintelligence, an AGI based purely on deep learning, will actually generate profoundly stupid and dangerous outcomes, because it will confidently drive us right off a cliff if that specific cliff wasn't represented in its training data. Taleb quips that in the fourth quadrant, it is highly important to know how not to become a turkey.
And to avoid becoming a turkey, to survive the fourth quadrant, you need something much more robust than just analyzing historical data. Which brings us to the final, perhaps most important framework in our deep dive, Judea Pearl, and his concept of the ladder of causation.
Judea Pearl is a Turing Award-winning computer scientist and philosopher. In his work, notably The Book of Why, he argues that the entire AI industry is stuck in a dead end because they are ignoring the mathematics of causality. He visualizes true intelligence as a three-rung ladder.
This ladder is such a clarifying way to understand the gap between AI and human thought. Let's break down the rungs in detail.
The first rung, the very bottom of the ladder, is association. The operational mechanism here is simply seeing and observing. It is finding statistical regularities in data. Mathematically, it is about conditional probability. What is the probability of event Y occurring, given that I have observed event X?
Pearl states very clearly that this first rung is where all current machine learning, deep neural networks, and many animals currently sit.
Yes, all of them.
The sources use the biological example of an owl hunting a rat. The owl observes how the rat moves, It finds the statistical regularity in the rat's path, and it associates the rat's current position with where it is highly probable to be 1 second later. It associates X with Y.
And that is exactly what a supercomputer playing Go does, just on a vastly larger scale. It studies a database of millions of board states to figure out which patterns are statistically associated with a higher percentage of wins. It is highly advanced, multidimensional association, but fundamentally it is still just rung one. It observes, but it does not truly understand.
So if multi-billion-dollar AI models are stuck on the bottom rung, what are the higher rungs? What does the math of actual intelligence require?
The second rung of Pearl's ladder is intervention. This moves from merely observing to actively doing. It requires an understanding of what will happen if you actively step into the environment and change a variable. Mathematically, Pearl represents this with a new operator, the do operator. It asks, what is the probability of Y occurring if I actively do X?
I want to make sure we don't gloss over the difference between observing X and doing X, because it is the core of causality. If I observe a barometer falling rapidly, I can associate that with an incoming storm. That's rung one.
Exactly. But if you physically smash the barometer with a hammer so the dial falls, does that cause a storm to arrive? No.
Right, because you just broke the instrument.
To understand intervention on rung 2, a system must possess a causal model of the world. It must understand the mechanics of cause and effect, not just the statistical correlation. It has to know that atmospheric pressure causes both the barometer to fall and the storm to arrive. A machine learning model trained only on observational data cannot distinguish between a falling barometer predicting a storm and a smashed barometer doing nothing.
Which perfectly explains why deduction and induction both struggle. Deduction doesn't care about the physics of the barometer, and induction just counts how many times the barometer fell before it rained. Neither one understands the invisible force of atmospheric pressure.
And it gets even more complex. The top rung, the third and highest level of causal thinking, is counterfactuals. This is the realm of imagination, retrospection, and understanding.
Counterfactuals. Asking what if.
Yes. It is the ability to look at a past event and ask, what would have happened if I had done something differently? Or would the patient have lived if they hadn't taken the medication?
A modern AI cannot do that. It cannot imagine a hypothetical reality that actively contradicts its training data. It can only predict the next word in a sequence based on past text. It cannot run a physics simulation of a counterfactual universe in its mind.
Pearl rigorously argues that machine learning can never supply real understanding because curve fitting and data analysis alone do not bridge the gap to the causal structure of the real world. You cannot simply scale up association, adding more layers to a neural network or more petabytes of training data to suddenly achieve the capability of imagination. Moving from rung 1 to rung 3 requires a fundamentally different mathematical and philosophical architecture.
Our sources quote Oren Etzioni, the head of the Allen Institute for Artificial Intelligence, to summarize this exact limitation. He bluntly calls modern big data systems high-capacity statistical models.
That's exactly what they are.
It is deeply impressive computer science. It generates incredible commercial value, but it fundamentally isn't intelligence.
Because it lacks common sense. And the sources bring up Alan Turing himself here, the father of computing. Turing noted that common sense is the invisible fabric that enables two human beings to simply engage in an ordinary conversation.
Right.
Truly understanding language or navigating a physical environment requires a deep causal understanding of the world, a nuanced appreciation of context, and the cognitive flexibility to detect and handle absurd abnormalities without shattering.
So we arrive at the ultimate question. If machine learning is permanently tethered to the bottom rung of Pearl's ladder, just correlating data points at superhuman speeds, does that mean all the current fever pitch hype about AI reaching artificial general intelligence is essentially a philosophical illusion?
If the industry continues to rely solely on the paradigm of induction, yes, it is an illusion. As our sources firmly conclude, to make genuine progress toward AGI, the field must look past induction. We have to look up the metaphorical ladder. We have to build systems capable of causal reasoning.
Wow. Okay, let's step back and recap this incredible journey, because we have covered immense philosophical and technical ground today. We started with the unyielding, crystalline mathematical certainty of deduction, Aristotle's syllogisms, and the dream of GFAI.
Right.
But we watched that certainty shatter when it collided with the messy, multifactorial reality of the physical world, perfectly illustrated by the overlapping pressures of the Boeing crashes. Deduction doesn't generate new knowledge, and it is entirely blind to relevance and causality.
So the scientific community pivoted to induction, learning from empirical experience, gathering massive data sets, and making probabilistic statistical predictions.
But then we discovered that induction conceals a fatal hidden flaw, the turkey problem. By assuming the mathematical distribution of the future will perfectly mirror the past, induction traps us in a brittle, fragile paradigm that completely falls apart when faced with the unprecedented.
It does.
We are currently building intelligent neural networks that can dominate closed, known games like Go, but they fail absurdly in the open real world, mistaking a school bus for a snowplow.
Yeah.
Because the real world is built out of fourth quadrant exceptions.
We have built powerful statistical engines, but we remain stuck on the bottom rung of the ladder of causation, completely devoid of intervention and imagination.
The sources drop one final, tantalizing hint right at the very end of the chapter. They suggest that true intelligence requires moving past both deduction and induction, towards something called abductive inference. Abduction is the cognitive ability to form the most likely coherent explanation for a totally novel, unprecedented event.
And that is a huge leap.
Right. And I want to leave you, the listener, with this thought to mull over. Think about your own human mind today. Imagine you walk out your front door this afternoon and you see a strange, unmarked package sitting conspicuously on your neighbor's porch.
Okay.
You don't calculate a Bayesian statistical probability based on a data set of 1 million previous packages. And you certainly don't sit down and write out a strict, formal mathematical proof to deduce its origin. In a fraction of a second, you instantly weave together the spatial context, your personal knowledge of your neighbor's habits, common sense about delivery routes, and your own imagination to form a causal hypothesis about what that object is and why it was left there. You use abduction.
You do.
Until a machine architecture is invented that can do that, until it can climb the ladder of causation and imagine a world it hasn't seen, well, maybe we shouldn't blindly trust it behind the wheel of a 2-ton car.
A profound and necessary thought to end our analysis on.
Thank you for joining us on this deep dive into the architecture of inference.